Hello everyone, and welcome to Natural Resources Canada's e-training module on fundamentals of life cycle costing for energy conservation. This course has been adapted from the U.S. Department of Energy's Federal Energy Management Program training material on life cycle costing for energy conservation. This training is being delivered through the Natural Resources Canada Greening Government Services to help federal departments and agencies plan and implement projects that reduce the energy use and greenhouse gas emissions in their buildings, laboratories, other facilities, and vehicle fleets. Over the years, Natural Resources Canada has developed comprehensive methodologies, practices, and tools to reduce energy consumption and greenhouse gas emissions for the private and public sectors, including the federal government. Since 1991, NRCan has provided enhanced technical support to Government of Canada organizations seeking ambitious greenhouse gas emission reduction actions from their building and fleet operations. This training will support federal organizations to meet their commitments and lead by example. Federal facilities have committed to reducing emissions from their operations by 40% below 2005 levels by 2025 and by 90% by 2050. As outlined in the 2020 Greening Government Strategy. It is important to note that federal buildings represent almost 90% of the government's greenhouse gas emissions. This initiative also supports the commitment by Canada's federal, provincial, and territorial First Ministers to scale up efforts to transition to highly efficient buildings and zero-emission vehicle fleets, as specified in the Pan-Canadian Framework on Clean Growth and Climate Change. Let's begin by reviewing the learning objectives for this course. At the conclusion, you will be able to use economic analysis to improve capital investment decisions and use common methods and assumptions to calculate life cycle cost analysis for federal projects. In the modules for this course, we will cover improving decisions using life cycle economics, what you need to get started, adjusting cash amounts to present value, how to calculate life cycle costs, how to evaluate efficiency levels among design alternatives, and how to allocate investment funding among competing projects. We'll start with Module 1, Improving Decisions Using Life Cycle Economics. In Module 1, we will discuss how life cycle costing can improve decision-making. Module 1 will include examples of decisions that can be improved using economic analysis, the principles of life cycle cost analysis, and the concept of economic optimization and how it relates to selecting the best energy efficiency solutions. So why is life cycle costing analysis important? Sound economic decisions by engineers, architects, and building managers are critical to improve the energy and environmental performance of buildings. Life cycle costing and related methods of economic analysis are a must for any energy-related investment decision. Life cycle costing analysis ensures that projects use resources cost-effectively, save energy and money, and provide the best value for taxpayer dollars. Life cycle costing analysis methods are recommended by the Greening Government Strategy for new construction projects and for major building retrofits. Departments should ensure that all new buildings and major building retrofits prioritize low-carbon investments based on integrated design principles and life cycle and total cost of ownership assessments, which incorporate shadow carbon pricing. The elements of performing a life cycle cost analysis are not overly complex. Many of the calculations can be completed using proven software programs to avoid mistakes and problems that can be confusing to energy and facility managers. An example of a software program that can be used for life cycle cost analysis is RETScreen, a clean energy management software developed by the Government of Canada. Life cycle costing analysis can assist with 5 major types of project-related decisions. These 5 types of decisions can apply to straightforward routine operating and maintenance procedures, as well as large multi-year capital planning projects. Let's look at each one of the 5. First, and perhaps most important, life cycle costing analysis can help determine whether to accept or reject a project based on its cost effectiveness. Second, life cycle costing analysis can assist in choosing a facility's optimal energy efficiency level. This allows you to determine which project options provide the optimal efficiency outcome. Third, life cycle analysis can assist in selecting or designing the optimal energy system for your facility. Fourth, life cycle analysis can assist in determining an optimal combination of interdependent systems to improve whole building performance. And fifth, Life cycle analysis can assist in prioritizing independent projects and to determine which are the best to fund. This is especially true when funding is limited and return on investment is critical. Is it worth it to replace or upgrade equipment? Will doing so save money and energy? The single most important economic criterion for capital investments that reduce future operating costs is straightforward. Savings must be greater than costs. You can determine this if you know upfront and investment costs. Next, let's take a quick look at some of the foundational concepts that will be used throughout this course and be discussed in detail in the following modules. The first concept is precisely what we mean when we talk about life cycle costing within the context of the federal sector. You need to understand that all life cycle cost analysis must take place within a predetermined and consistent study period. The study period may be short or long, but must be the same for all project alternatives. Within the study period, it is important to also establish and recognize and adjust cost values for the time value of money. When the study period and time value of money are established, you can identify your base case and learn how to evaluate project alternatives. We will also cover the comparison of investment costs with operating costs in order to calculate accurate life cycle costs. Now let's define some key life cycle costing concepts. Life cycle costs are the sum of present values of investment costs, capital costs, installation costs, energy costs, operating costs, maintenance costs, and disposal costs over the lifetime of the project, product, or measure. The study period is the predetermined time during which alternative project scenarios are evaluated against the current operating scenario. The study period begins at the base date and reflects the expected lives of the systems. The study period must be the same among all alternatives. Base case is the current operating scenario. The alternative is the hypothetical scenarios being evaluated against the base case during a common study period. This course uses the term alternative to include the base case when discussing the life cycle cost method in a general way. The concept of time value of money recognizes that the value of money is tied to time. $1 today does not have equivalent value to $1 in the future. In life cycle cost analysis, all costs must be adjusted to place all dollar values expended or received over time on a comparable basis before assessing a project's life cycle costs. Investment costs include initial investment costs, replacement costs, and the residual value of the project. Operating costs include costs related to operation, maintenance and repair, and energy. So what is life cycle cost? Life cycle costs are all costs associated with the installation, operation, and maintenance, and replacement of individual equipment and systems over the entire lifetime of a project. Life cycle cost analysis allows you to calculate these totals and directly compare alternative investment options. Let's walk through the different project costs that add up to a total life cycle cost. First, initial investment costs occur at the beginning of the study period. Second, operations, maintenance, and repair, also known as OM&R costs, such as energy, routine maintenance, and periodic repair costs, occur continually throughout the study period. Third, planned replacement costs, like replacing an HVAC system, occur at scheduled times during the study period. Fourth, at the end of the study period, there may be a residual or remaining value for the equipment or systems. These costs will need to be adjusted for what is called the time value of money. This adjustment is necessary to determine present values because these costs occur at different times. The sum of all these adjusted values is called the total life cycle cost. Calculating life cycle costs will provide the clearest picture of all costs associated with a project. Let's look at an example of a heating system. The initial purchase cost of the system itself is only about 7% of the overall cost. Maintenance and repairs account for approximately 16% of the total costs, but over the 15-year period, energy consumption accounts for 78% of overall costs. You can see it is critical to understand all the costs associated with the life cycle of the project. First costs can often be just a small part of the bigger picture. Now let's look at the life cycle costs of two alternative options, A and B. Alternative A represents the status quo based on current equipment and efficiency levels. This is called the base case. Here, Alternative A has lower investment costs and higher operating costs over the study period. Alternative B is an option to invest in more efficient equipment and decrease operating and energy costs. Alternative B carries additional upfront investment costs because the equipment has higher energy efficiency. In alternative B, the decrease in operating costs over the study period more than offsets the increase in initial investment costs. Therefore, overall life cycle costs are actually reduced. Even though initial first costs are higher, the best choice is alternative B. Now that we know that the initial purchase price may be a small part of total costs, let's look at the three main ways to evaluate the optimum level of investment in a typical economic analysis. These include investment versus operating cost analysis, incremental or marginal cost analysis, and net savings analysis. The first way to determine the optimal level of a system is by the analysis of an investment versus operating cost. The x-axis of this diagram shows a range of energy efficiency levels for a particular facility, with energy efficiency increasing from left to right. The y-axis represents costs, including investment in OM&R costs. As the project's energy efficiency increases, operating costs decrease and investment costs increase. Q indicates the optimal level of energy efficiency that will provide the project's lowest life cycle costs. This point, Q, is where the sum of investment and operating costs is the lowest. A second way to determine the optimal level of investment is by looking at incremental or marginal costs and the savings associated with improving energy efficiency. The diagram shows Q as the optimal energy efficiency level. This is where the incremental investment costs are equal to the incremental savings from the energy costs. At this level, total life cycle cost is at its lowest. Every dollar spent up to the point Q has led to cost savings greater than $1, while investing an extra dollar beyond Q will lead to cost savings less than the dollar invested. A third way to determine optimal level of investment is by net savings analysis. This graph shows the most cost-effective level of energy conservation can also be determined by finding the level that maximizes net savings. Net savings is the difference between total costs and total savings. Here, the investment cost curve is identical to the one in the previous slide. It is compared against an operating savings curve. The operating savings curve is determined by taking the difference between the operating cost at zero level of investment and the operating cost at any other level of investment. The economically optimal level of energy efficiency Q is where net savings is greatest. We have finished Module 1 and will move to Module 2, Getting Started. In the first module, we learned about the principles and requirements of life cycle costing. In this module, we will discuss how to get started with the life cycle costing analysis process. The best way to kick off the life cycle costing analysis is to take time to identify and organize basic project information. Each of the following steps is critical to ensure success. 1. Define the problem and project objectives. 2. Decide on the amount of time and level of effort needed for the life cycle costing analysis. 3. Choose the method to document your process. 4. Identify feasible project alternatives. 5. Specify which data will be required to analyze the alternatives. 6. Identify reliable data sources. Life cycle cost analysis results will only be as accurate as the data inputs. 7. Select a specific study period to use consistently for all alternatives. And 8. Draw a cash flow diagram to illustrate the monetary timeline for each project alternative. A cash flow diagram is a simple and effective way to visualize the most important costs. It will prove to be an essential point of reference throughout the process. Now let's learn about each of these critical steps. Let's start with preliminary considerations. The first step in the life cycle costing process is to identify the problem and project objectives. Are you dealing with a poor performing piece of equipment that needs replacement? Do you have a given level of funding that you need to use optimally in order to get the greatest returns on your investment? Make sure from the outset that you define the current situation and state the desired outcome. Next, think about level of effort. Depending on the project scope, life cycle costing can be very time-consuming and detail-oriented, or it can be used for very simple and quick calculations. The level of effort should be tailored to the needs of the project. Life cycle costing studies, both small and large, need to be carefully documented to keep track of where you are in the evaluation process. Document your work so it can be replicated and checked for errors. The extent of documentation should reflect the complexity and scale of the project. Items to be documented in life cycle cost analysis include project description, alternatives, common parameters, cost data and related factors, calculations, interpretations, non-monetary savings and costs, other considerations, and savings and recommendations. Now we will discuss choosing between project alternatives. In economic analysis, alternative is the term used to describe a hypothetical improvement project that can be compared to the current operating scenario or base case. There are 3 key points to take into account when choosing project alternatives. First, make sure that each alternative you choose is strong. Your decision can be no better than the best alternative you consider, no matter how good your economic evaluations. Second, only consider alternatives that satisfy performance requirements. When doing so, take into account constraints such as availability of energy sources and building code requirements. Do not include in your economic evaluation alternatives that have to be rejected on other grounds. Third, account for additional gains that may be realized but are not directly related to performance. Remember that life cycle costing is an economic model and will not account for non-monetary benefits. While some values might be initially difficult to quantify, it is necessary to determine if they should be included in the assessment, and if so, what they are worth. For example, it may be important to lower the project's environmental impact, including measures that conserve natural resources. These types of environmental benefits may not have clearly associated dollar amounts. Nevertheless, they should be documented up front so they are not overlooked later on. Now that you've identified the most viable project alternatives, you are ready to determine relevant effects for each. Start by identifying the significant or relevant costs associated with each alternative. Only costs that change from one alternative to another should be evaluated. Focus on collecting data that are likely to have a significant effect on the life cycle costs of an alternative. Costs that remain the same do not increase or decrease the life cycle costs of an alternative relative to the base case and therefore do not need to be included. For example, if 2 different pieces of equipment have the same maintenance and repair costs, do not include these costs in your analysis because they are identical. Likewise, if these maintenance and repair costs are minimal or non-existent, ignore these costs. Unless costs have significant value with significant impact, exclude them from your analysis. This will save time and effort and result in the same conclusion. Also, do not take into account sunk costs or costs from a decision that has already been made. For example, if a piece of equipment has already been installed, do not take into account the costs because these costs were incurred before the study period. As such, they are already built into the analysis. Let's discuss how to identify costs and benefits. Several different costs and benefits must be taken into account in life cycle costing analysis. Investment-related costs include the following: acquisition costs, which are sometimes referred to as the first costs of purchasing equipment; replacement costs, which are incurred when equipment is replaced during the study period; and residual value, which is the remaining value of the equipment at the end of the study period. Operational costs include the following: operation and maintenance costs to be included for the particular alternative being considered. Repair costs include scheduled or on-schedule repairs that keep equipment running according to specifications and are incurred in addition to routine operating and maintenance costs. Energy costs are these costs associated with energy consumption, including electricity, natural gas, and fuel oil. Water costs are also included in this category. Other costs or benefits can factor into the life cycle cost analysis. These can include revenue from installing equipment that generates income, utility rebates or tax credits given for energy efficiency improvements, federal or provincial tax credits applied to offset costs associated with the project. There are also non-quantifiable costs and benefits. These include environmental impacts from energy and resource conservation, work productivity, and occupant health and comfort. Many of these costs and benefits are difficult to quantify, but often need to be considered in life cycle cost analysis. Valid LCC analysis requires that all costs and benefits be estimated in current base year prices. These base year amounts will be multiplied by discount factors that incorporate any applicable escalation rate and the discount rate to adjust for their occurrence at different times during the study period. Effects not expressed in dollars are not included in the measures of economic performance. Cost estimates for the initial purchase and replacement of equipment are available through a number of different sources. Talk to your supplier for federal facilities or contact a pre-approved supplier to request a quote for equipment costs. Equipment costs can also be found in databases such as RS Means, These include the average cost data for different equipment types and activities for building construction, maintenance, and repair. Use your professional experience or the experience of a coworker to estimate costs for replacing equipment based on previous work completed on the project. Examine historical data for relevant costs that were incurred in the past at your particular facility. Continuing to estimate costs in today's price, the next step is to determine the quantity of energy that will be consumed under each alternative. There are a couple of different ways to do this. One option is to manually estimate the energy used based on your facility's historical data and to extrapolate its future energy use by the relative impact of the alternatives improvements. Another option is to use energy modeling software or advanced building automation systems to make these estimates. Then, identify current prices related to each alternative's energy use pattern. In addition to using your facility's current rates, identify the rate type and rate structure to determine how costs will vary with changing consumption patterns. Finally, calculate price escalation for future energy consumption, because the prices for energy will change significantly over time. Obtain price projections from your utility company. These forecasts should be used to accurately determine current and future energy costs. Now that current and future costs associated with project alternatives are established, next determine the length of the study period. It's important to adhere to the same study period for all project alternatives. Choose the appropriate study period. The first consideration is to accommodate the investor's time horizon. Depending on the investor, the time horizon may be short, perhaps 5 to 10 years, or long, up to 40+ years. The time difference will have a significant impact on the results. The useful lives of the equipment and systems being installed are also a major consideration. Often, the appropriate study period length is directly linked to the useful life of the equipment. The service period begins when the project commences or when occupants begin to use the facility. It is often useful to draw a simple cash flow diagram to show the type and timing of costs that have been identified for each alternative. Key dates can be entered to indicate the base date, the service date, and the end of the study period. The cash flow diagram provides a visual checklist of relevant effects and their timing. Your diagram will vary based on whether the project is turnkey or phased in. Here is a cash flow diagram for a turnkey project that is handed over at completion. Time and costs for upfront planning, design, and construction occur before the base date of the study period. These initial investment costs occur in a lump sum on the base date when the building is occupied or the system is taken into operation and energy costs and other operational costs begin to accrue. Energy and OM&R costs occur periodically until the end of the study period in year N. In contrast to a turnkey project, in a phased-in project, the initial investment costs occur over several years. The analyst may choose to phase in the initial investment costs over a multi-year period for design, planning, and construction. This cash flow diagram reflects a phased-in project. The initial investment costs for planning, design, and construction are spread out over several years. Initial investments are made in years 1 to 3, and system operation begins in year 4. That concludes Module 2. In Module 3, we will discuss methods for adjusting cash amounts to reflect present value in life cycle costing calculations. In previous modules, we discussed the basic concepts behind life cycle costing and how life cycle costing analysis can assist you in making the best economic decisions for your facility. This module will further clarify life cycle costs and equip you to make accurate LCC calculations. Based on these lessons, you'll be able to understand how to discount cash amounts to the present value, find the correct present value factors for different applications, and choose the correct method for handling inflation in life cycle cost analysis. Let's start by learning how to discount costs to present value. Here is a familiar cash flow diagram. As you can see, there are certain costs associated with particular project phases throughout the study period. These include initial investment costs up front, recurring energy and OM&R costs annually, replacement costs at year 4, and residual value at the end of the study period. Before we can compare or sum costs occurring at different points over the study period, we must convert all costs to a common point in time in order to reflect the time value of money. This conversion process is called discounting. Usually, future costs or savings are discounted to present values so they can be directly compared with initial investment costs. Now we will discuss ways to calculate the time value of money. The discount rate is the interest rate that makes an investor indifferent between cash amounts received from different points in time. This is the rate of interest you would have to receive to make the dollar amount in the future equivalent to the current dollar amount. We will look at three types of the cost conversions for discounting costs. First, single non-recurring future costs, such as a one-time replacement cost, occur once in the future and should be adjusted to present value. Second, annually recurring uniform costs, such as scheduled operations and maintenance costs, occur year after year in approximately the same cost amount each year. Third, annually recurring non-uniform costs, like energy costs, recur every year, but cost amounts vary from year to year. In other words, the cost of electricity may vary, but occurs year after year. Please note that the energy costs and operations and maintenance costs used in this course serve as an example only. Costs are specific to a jurisdiction and project, so please be sure to select the costs that are appropriate to your project when conducting a life cycle cost analysis. Let's step through how to calculate the discount rate. First, you can calculate the discount rate if you know the present value and future value. In formulaic terms, the discount rate equals the future value, FT, divided by the present value for what it is worth in current dollars, all to the 1 over T minus 1. As an example, assume you are looking at the time frame of 10 years. Your cost's present value is $100 and its future value is $216. So at the end of 10 years, you receive $216. You can plug these values into the equation to calculate a discount rate of 8%. In other words, if an item costs $100 this year and you get 8% on that value every year for the next 10 years, you will have $216 in 10 years. Next, you can also adjust the same equation to solve for the future value. If you know the present value and the discount rate, you can calculate what future value would be equivalent to the current value. In this example, we will use the same 10-year study period, 8% discount rate, and present value of $100. Multiply that by 1 plus the discount rate to the 10th power. That calculates to be 100 times 2.16, and that equals the $216, the amount we calculated previously. This value of 2.16 represents the single compound amount, or SCA. When multiplied by the present amount, the SCA produces the future value. Finally, you can also calculate the present value if you know the future value and the discount rate. For instance, if the future value is $216 and you know that your discount rate is 8%, you can use this adjusted equation to solve for the present value. In this case, $216 in future value is equal to $100 in current value. The factor that can be multiplied by the future amount to determine the present value is called the single present value, or SPV. If you know the future dollar value and the discount rate, you can simply multiply the future value by the SPV to find the present value. Here we see how to compute the present value of a series of cash amounts that occur annually over a given study period and are the same each year. This may look like a complex equation, but it actually simplifies down very easily. The first equation shows the cash amount in each year discounted individually, and all the resulting present values are summed to arrive at a present value for the entire stream of costs. By rearranging the terms, you arrive at the closed-form equation whose bracketed part produces the Uniform Present Value Factor, or UPV. This UPV factor is multiplied by the uniform annual amount to get the present value of the entire stream of cash flows. In our example, the annual recurring cost in the first year of $100 is represented by A sub 0. The discount rate remains 8%, or 0.08, which is then added to 1 to produce 1.08. The resulting value of 6.71 is the Uniform Present Value Factor, or UPV, for the multi-year cost time frame. To receive the total present value, multiply the UPV by the annual uniform recurring cost. This is an important equation as you will have to calculate UPV when calculating present value of a series of cash amounts that are uniform and occur annually over your study period. Sometimes recurring annual amounts are not uniform. They change from year to year at some known annual escalation rate, represented by the small e. Energy costs are a good example of a non-uniform recurring annual cost. This rate of change can be either positive or negative, but usually reflects price increases over time. Again, the present value can be computed for the cash amount in each year, and summed or a closed form equation can be used to calculate the present value. The factor produced by this equation is called the modified uniform present value, or UPV** factor. This can be multiplied by the base annual amount, the annual amount as of the beginning of the study period, to get the present value of the entire stream of cash flows. We will continue to use the same example and assume that the escalation rate is 3% a year, which means that our initial cost of $100 escalates by 3% a year. The value we receive, when we plug in the variable and solve, is the modified uniform present value, or UPV*. The star means the escalation is taken into account. In this example, we receive a UPV* of 7.777. To solve for the present value, multiply this UPV* value by the $100 for each year to get $778 total for the 10-year time frame. Again, this equation is important if you have a series of recurring annual costs that are not uniform in your study period. Let's move on from calculating present value by discussing the impact of discount rate selection. The discount rate can greatly impact the life cycle cost estimation of a project. For federal projects, the discount rate is normally between 2 and 3%. This value is calculated based on the economic conditions for a given year and will change over time. Be sure to check with your department about the appropriate discount rate to use for your project. This chart illustrates a simple example of how $1 in present value terms changes over time. For instance, in year 7, $1 is equivalent to about 80 cents, given a 3% discount rate. This value drops to about 60 cents at a 7% discount rate and 50 cents at a 10% discount rate. As you can see, the greater the discount rate, the less the dollar amount will be in future. If you want to use an alternative discount rate that is closer to the return on investment in the stock market, the correct discount rate will be closer to 10%. So far in this module, we have discussed two important concepts: discount rates and cost conversion factors. Now, we will discuss the third important aspect of this module: inflation, which reduces the purchasing power of the dollar over time. This simple graph illustrates inflation. For example, $1 in 1990 has a different value than $1 in 2000. Dollars expended in different years, with different purchasing power, cannot be added together directly to arrive at a meaningful amount. In addition to accounting for the time value of money using a discount rate, economic evaluations must also account for the change in purchasing power over time using the inflation rate. To start, let's define 5 key terms related to inflation: price inflation, price escalation, differential price escalation, constant dollars, and current dollars. These terms will be used frequently in the following discussion on how to treat inflation in an economic analysis of capital investments. Price inflation is the rate of increase in the general level of prices. Price escalation is the rate of increase in the price of a commodity, for example, electricity prices. Differential, or real price escalation, is the rate of increase in the price of a commodity relative to inflation. Constant dollars are dollars of uniform purchasing power, exclusive of general inflation, and current dollars are dollars of purchasing power in which actual prices are stated, inclusive of general inflation. Two approaches exist for handling inflation. The calculation can either include general price inflation or exclude it. In the first approach, include general price inflation by specifying all costs in current dollars and use a nominal discount rate and a nominal escalation rate, both of which take inflation into account. Alternatively, you can exclude general price inflation and specify all dollars in constant dollars. Here, use the real discount rate and real escalation rates to exclude inflation. Cash flows can be stated either in current dollars or in constant dollars. The constant dollar method of inflation adjustment is preferred for full funded projects, which generally do not consider taxes, mortgage payments, or year-to-year budget disbursements expressed in current dollars. The current dollar method is preferred for finance projects, where contract payments are calculated with market interest rates that include inflation. Mathematically, both approaches lead to the same present value. Both constant and current dollar analysis will yield exactly the same present value result and thus support the same conclusions. Let's discuss how to derive the real discount rate. Here is the basic formula for calculating the real discount rate using nominal discount rate and the rate of general inflation. In the formula, the nominal discount rate is capital D, the rate of general inflation is capital I, and the real discount rate is the lowercase d. The real discount rate is 1 plus the nominal discount rate divided by 1 plus the inflation rate minus 1. You can transpose the same formula to solve for the nominal discount rate, which is just 1 plus the general inflation rate times 1 plus the real discount rate minus 1. Here is a simple example to calculate the real discount rate. Assume you know the nominal discount rate at 3.9% and the inflation rate is 0.9%. Plug these values into the equation to arrive at a real discount rate of 2.97%. In this example, the real discount rate is lower than the nominal discount rate since inflation is positive. You can use the nominal or real discount rate to calculate the present value of a one-time cost in year T. First, when costs are provided in current dollars, the nominal discount rate should be used. To find present value, multiply the cost in year T by 1 over 1 plus the nominal discount rate to time T. Alternatively, when costs are in constant dollars, the real discount rate should be used. To find present value, multiply the cost in year T by 1 over 1 plus the real discount rate to time T. The escalation rate will need to be taken into account when estimating a future cost given a present value. We calculate this in a similar way to the discount rate. To estimate the future cost in year T, when costs are in current dollars, use the nominal escalation rate. To calculate the future cost, multiply the cost in year 0 by 1 plus the nominal escalation rate to year T. To estimate future cost in year T, when costs are in constant dollars, use the real escalation rate. To calculate the future costs, multiply the cost in year 0 by 1 plus the real escalation rate to year T. To calculate a present value using current dollars, use nominal discount and escalation rates. In this equation, take the cost times 1 plus the nominal escalation rate divided by 1 plus the nominal discount rate to the year T. Alternatively, use constant dollars. Take the cost times 1 plus the real escalation rate divided by 1 plus the real discount rate to the year T. The key here is to be consistent with the rates. It is possible to derive the real escalation rate based on the nominal escalation rate and the general rate of inflation. To do so, use a similar approach as the one used in the calculation of the real discount rate. The real escalation rate is 1 plus the nominal escalation rate divided by 1 plus the general inflation minus 1. You can solve for the nominal escalation rate if you know the general inflation rate and the real escalation rate. Here is an example of how to calculate the real escalation rate. If you know that the nominal escalation rate is 6% and the general inflation rate is 4%, you can enter them into the formula to solve for a real escalation rate of 1.923%. This example shows nominal price escalation that includes general inflation. Here we assume a general inflation rate of 4% and nominal escalation rate of 6%. When the escalation rate decreases, the overall price factor also decreases as the rate drops from 4% to 2%. The variation can be significant over 10 years based on what the escalation rate happens to be. This graph shows that the estimated escalation rate can have a big impact on your results. Let's work through an example of how to calculate the present value of one-time cost with inflation using nominal rates and then real rates. This example first uses nominal rates, then uses real rates, and then shows that the same present value is realized, and the results are the same as long as you are consistent with using nominal or real rates. First, make the calculation using nominal rates. Here there is a nominal escalation rate of 6%, a discount rate of 8%, and we get a cost C sub-zero that is $100. If you plug in those values into the equation for the nominal rates, you get a result of $82.95. Next, make the calculation using real rates. When we use the values calculated previously and plug in the numbers, you have $100 times 1.01923 divided by 1.03846 and once again, you get the same result of $82.95. That concludes Module 3. In Module 4, we will cover how to calculate life cycle costs of projects. In the first module, we talked about economic optimization and the primary concepts behind life cycle cost analysis. We followed up in the second module with a discussion of specific data requirements and sources for data to get started. In Module 3, we discussed the importance of adjusting cash amounts to present value using discounting factors. Now you are prepared to actually calculate life cycle costs. In this module, we will cover two fundamental objectives. First, we will calculate the life cycle cost of alternative projects. Next, we will choose the correct method for handling inflation in a life cycle cost analysis. We will look at these two fundamental objectives using two basic funding options: projects that are fully funded upfront and finance projects such as energy performance contracts or EPCs. What are life cycle costs? Life cycle costs include all costs associated with the installation, operation and maintenance, and replacement of individual equipment and systems over the entire lifetime of a project. Life cycle cost analysis allows you to calculate these totals and directly compare alternative investment options. Let's walk through different project costs that add up to a total life cycle cost. First, initial investment costs occur at the beginning of the study period. Second, operating maintenance and repair costs, or OM&R costs, such as energy, routine maintenance, and periodic repair costs, occur continually through the study period. Third, replacement costs, like replacing an HVAC system, occur at scheduled times during the study period. Fourth, at the end of the study period, there may be a residual value for the equipment or systems. You've already learned that all costs need to be adjusted because they occur at different times. The sum of all these adjusted values is called the total life cycle cost. At first, the general formula for calculating life cycle costs may look daunting. Let's walk through the equation and then discuss how terms can be simplified. Life cycle costs represent the sum of all project costs appropriately discounted to present value. In this equation, the costs for each year of the study period are represented by the numerator C. Discounting for each year's costs is represented by the denominators. When you sum all those, you can condense the equation into the summation of costs. Calculating life cycle costs does not need to be complicated. Grouping costs by type can help simplify the process. Just remember that costs must be discounted to reflect the actual value of money at a given time. It might be easiest to think of LCC as the sum of all investment costs and operating costs. Investment costs include initial costs, replacement, and residual costs. Operating costs include energy costs, as well as operation, maintenance, and repair costs. Total investment cost equals initial investment costs plus a replacement cost minus any residual value. Total operating costs equals energy cost plus the operations, maintenance, and repair costs associated with the project. The next part of the module will look at how to calculate these values for two types of projects: fully funded and financed. First, we'll walk through how to calculate LCC for a fully funded project, which typically receives all initial investment costs in a lump sum at the base date. The LCC for fully funded projects should use constant dollar analysis with a real discount rate and real energy price escalation rates. Here is an example that shows how to calculate the life cycle cost for a fully funded project. In this example, we use a heating and cooling system for a small office building. The base case is the existing central direct expansion cooling system with electric heat. The alternative will replace this system with a heat pump. We will use a discount rate of 3% for the real rate and 3.5% for the nominal rate. The costs and benefits will be stated in base year dollars. We will use an electricity price of 13.08 cents per kilowatt hour. Note that you should use your local electricity and commercial rates. The discounting convention is end of year. Let's determine the data inputs for each alternative. For the base case, we will assume current equipment has been maintained and there are no required purchasing or installation costs. There are zero replacement costs because the equipment is maintained throughout the study period. The equipment will be at the end of its useful life by the end of the study period, so there will be no residual value. It currently uses 19,800 kilowatt hours of energy annually at 13.08 cents per kilowatt hour. There are annual recurring maintenance costs of $350, and the air conditioner equipment requires repair in year 10 at a cost of $1,500. Both the remaining useful life and study period for the equipment is 15 years. Therefore, at the end of 15 years, the equipment will have no remaining value. Now, let's list the data inputs for the alternative case. The alternative to the base case is to install a heat pump system to replace the old system. Because you are purchasing the equipment and installing it, there will be an initial upfront cost of $2,841. There will be no replacement costs because the useful life of the equipment is 20 years, and this is a 15-year study period. There will be some residual value in the equipment because there are 5 years, or 25%, of useful life remaining at the end of the study period, which equals $710 of the initial cost. If you install this heat pump system, the electricity consumption will now be 16,290 kilowatt hours at the same electricity price of 13.08 cents per kilowatt hour. The annual maintenance cost for this equipment will be $450, and the compressor and the heat pump will have to be repaired in year 8 at a cost of $1,200. Now we will calculate the life cycle costs for the base case and alternatives. Remember that life cycle cost equals the present value of the initial investment costs plus the present value replacement cost minus the present value of any residual value plus the energy costs over the study period plus any operations, maintenance, and repair costs. Now let's plug in the values for each alternative and calculate the LCC for each. Then we'll compare and choose the best option. In the base case, you have an initial investment cost of 0, replacement cost of 0, and residual value of 0. The present value energy cost is $2,590. To determine the future cost of energy, multiply $2,590 by the Uniform Present Value, UPV, star factor for electricity in commercial buildings for 15 years. In this example, the value is 11.25. Operations, repair, and maintenance costs are $350 a year for 15 years. To calculate the future value of these costs, multiply $350 by 11.94, which is the UP value for 15 years at the standard 3% discount rate. Next, discount the repair cost of $1,500 in year 10 using the single present value of 0.744. Add the two adjusted OM&R related costs together. The total life cycle cost is the sum of the first three values plus the energy costs plus the OM&R costs. When you add these, it gives you a total life cycle cost of $34,433. Now, we'll use the same process to determine life cycle costs for the alternative heat pump installation. In this case, there is an investment cost of $2,841. There is no replacement cost. There is a residual value of $710 that must be discounted back to a present value using the appropriate SPV factor of 0.642, which corresponds to a 15-year study period at the 3% discount rate. Energy will cost $2,131 a year. To adjust this amount, use the same UPV star factor of 11.25 as the previous example for commercial electricity rates for 15 years. Like the previous example, there are maintenance costs of $450 a year. Use the same UPV factor that was used in the previous example of 11.94 to adjust this amount. There is also a repair cost of $1,200 that can be adjusted using the single present value for year 8 of 0.789. Sum these to determine the life cycle cost of $32,679 for the alternative. Now that we have calculated the life cycle cost for both cases, we can determine the net savings that results. To calculate the net savings, subtract the alternative life cycle cost from the base case life cycle cost. This results in a net savings of $1,754. In this example, it is clear that the alternative is more life cycle cost effective than the base case. Unlike fully funded projects, initial costs for finance projects are phased in during a planning or construction period. The next example calculates LCC for a finance project and uses current dollar analysis with a nominal discount rate and nominal energy price escalation rates. In this example, we will examine how to calculate LCC and net savings for a finance project using third-party financing such as an EPC with a fully amortized loan. As in the previous example, the loan amount would be for the initial investment cost for $2,841. That loan amount would be paid off over the contract term of 10 years at a 6% borrowing rate and lead to an annual contract payment for principal and interest on the loan of $386. All other costs associated with the project will be exactly the same as the fully funded project. These examples only differ in how they are financed and paid. In the case of the heat pump alternative, the only cost that changes relative to the previous example is the initial investment cost. In the case of project financing, this cost will be zero. There will be an annually recurring contract payment of $386 for 10 years. To calculate this, you need to calculate the UPV for 10 years at a 3% discount rate. Keep the remaining the same as if you paid with department funds. When you add up all this cost, you get $33,131. To calculate the net savings for the alternative project, subtract the LCC of the alternative from the LCC for the base case. The net savings of financing the project as opposed to the base case is $1,302. That concludes Module 4. In Module 5, we will learn how to evaluate different efficiency levels among design alternatives. In this module, we will explore how to find the alternative with the highest efficiency for the lowest life cycle cost. This is called simultaneous optimization. We will use 3 examples to illustrate the concept. At the conclusion of the module, you will be able to determine the efficiency level with the lowest LCC, determine the independent system or design with the lowest LCC, and evaluate interdependent systems to minimize LCC. From an economic standpoint, optimization means finding the design alternative and performance level with the lowest life cycle cost. Whether evaluating a single system independently of other systems or several interdependent systems simultaneously, the general rule for simultaneous optimization is the same. Find the design alternative and performance level with the lowest life cycle cost. Good examples include level of insulation to be installed in a roof, wall, or floor of a building, level of thermal performance for window systems, efficiency of a furnace or boiler, energy efficiency ratio, or SEER, for an air conditioner or heat pump system, and collector area of a solar heating system. Now we will look at an example that involves optimizing interdependent system alternatives with the goal of discovering the best combination. Since a facility has multiple systems that affect each other, it is important to account for these interactions. In many cases, the lowest LCC alternatives may change when other independent systems are modified. For instance, if the building envelope becomes more thermally efficient, the savings from HVAC system improvements will diminish and vice versa. Here is the equation representing the general rule for simultaneous optimization. This formula can be used to find the best combination of all options. This formula represents the large number of combinations required to find the lowest overall life cycle cost. I stands for the system combination, S for the building system or baseline, and J for the alternative system. For a particular system combination I, sum the present value costs for all N systems, where present value costs equal investment costs, plus replacement costs, minus residual value, plus OM&R costs, plus energy costs for that particular system combination. Next, let's look at another example. Here we will determine the optimal combination of 3 interdependent systems: HVAC type, wall insulation R value, and window glazing options. The system design alternatives will be the same as in the previous examples for the HVAC system and wall insulation. For window glazing, we will consider 3 options. First, double glazed. Second, double glazed with low E. And third, double glazed with low E and argon gas fill. These tables calculate the cost for each system alternative and the combined life cycle costs. The combination with the lowest life cycle cost is highlighted in bold on each table. For the first system, central AC with propane, the best option is R11, wall insulation and double pane windows with argon fill at a cost of $47,322. For the system with central air conditioning and electric heat, the best option is R11 wall insulation with double glazed windows at a cost of $41,659. We continue to determine the optimal combination of systems. The lowest life cycle cost combination for the natural gas system is R11 insulation with double glazed windows at a cost of $40,567. The best option for the heat pump alternative is the R11 insulation with double glazed windows at a cost of $37,695. Now, we can compare all HVAC system options and select the one with the lowest LCC. The heat pump option with R11 wall insulation and double glazed windows has an LCC of $37,695, the lowest of all the available options. Therefore, this is the optimal combination to select. You can use several strategies to assist with simultaneously optimizing interdependent system alternatives. First, decrease the number of alternatives under consideration by finding the lowest LCC alternative for each system using a best guess for specifications of other systems, and considering only practical and balanced combinations of project alternatives. For instance, it might be unwise to first add PV to a building with uninsulated walls. In most cases, it would be more cost-effective to install insulation first and then add PV to offset already reduced costs. Second, investigate how sensitive the lowest life cycle cost alternatives are to energy prices. If energy prices rise even slightly, how are the systems impacted in combination? You should also investigate each alternative's sensitivity to other system specifications, because some systems are linked more strongly than others. For instance, envelope systems, such as walls or windows, tend to be weakly linked. On the other hand, the connection between the building envelope, lighting systems, and HVAC systems are much stronger. Changing one will have a significant impact on the other. These strategies are not mutually exclusive or sequential. Use one or more in the order that will benefit your project most. That concludes Module 5, and we move to Module 6 on allocating investment funds among competing projects. What happens when you determine that multiple project alternatives are life cycle cost effective? How can projects be prioritized so the best decision for allocating project funding can be made? This module will introduce the best methods to select options among mutually exclusive projects to match your budget. Throughout this course, you have learned how to calculate life cycle costs and supplementary economic measures and select mutually exclusive project alternatives. This module will demonstrate how to allocate a budget and rank independent projects according to savings to investment ratio. It will also demonstrate how to allocate a budget between a combination of independent and mutually exclusive projects for both one-time funding opportunities and funding that will continue year after year. The key is to select a combination of projects with the greatest savings to investment ratio, which will lead to the maximization of net savings. Let's start off with a simple example that assumes a $20,000 budget. This slide shows 4 projects, A, B, C, and D. Each project has varying investment costs, energy savings, and energy cost savings. For example, Project A has an investment cost of $10,000, energy savings of 100 gigajoules, and $20,000 of present value energy savings. However, Project D has an investment cost of $5,000, energy savings of 220 gigajoules, and $11,500 of present value energy savings. All 4 projects are life cycle cost effective. However, the 4 projects combined will cost $30,000 in present value terms, $10,000 over your budget, which means not all projects can be undertaken. The key here is to use the appropriate approach to rank the projects to maximize net savings. We will consider 3 approaches to emphasize this point. 1. Energy saved per dollar of investment. 2. Net savings. And 3. Savings to investment ratio. The net savings for the $20,000 budget will vary according to the ranking method implemented. The first approach is to rank the projects by energy savings per dollar of investment. To calculate this value, divide the energy saved by the amount invested in the project for all 4 projects. Project A has an investment cost of $10,000 and energy savings of 100 gigajoules. Therefore, it has 10 gigajoules saved per $1,000 invested, or 0.01 gigajoules per dollar invested. Another project in this example, Project B, has an investment cost of $10,000 and energy savings of 1,000 gigajoules. Therefore, it has 100 gigajoules saved per $1,000 invested, or 0.1 gigajoules per dollar invested. In this approach, Project B has the greatest amount of saved energy per dollar invested, with 100 gigajoules saved per $1,000 invested, followed by D, C, and then A. The second approach is to rank the projects by net savings. You've learned that net savings is calculated by subtracting the initial investment costs from the present value of future savings. Project A has an investment cost of $10,000 and $20,000 of present value energy savings. Therefore, it has net savings of $10,000. Project B has an investment cost of $10,000 and $17,000 of present value energy savings, with net savings of $7,000. When you rank these projects from greatest to smallest net savings, Project A comes in at $10,000, followed by Project B, D, and then C. You'll note that this ranking differs from the energy savings approach. The third approach is to rank the projects by savings to investment ratio. In this approach, simply divide the savings by the investment costs. Project A has an investment cost of $10,000 and $20,000 of present value energy savings. Therefore, it has an SIR of 2. Project D has an investment cost of $5,000 and $11,500 of present value energy savings. It has an SIR of 2.3. The greatest SIR belongs to Project D with an SIR of 2.3, followed by C, A, and B. Now we are ready to compare the project rankings. This chart calculates the total net savings for each of the 4 projects according to each of the 3 approaches. Remember that you will only be able to select 2 or 3 projects given your $20,000 budget limitation. In the first column, we use the energy savings per investment method with projects B, C, and D. Using this approach, we will add the net savings per investment for each project, $7,000 plus $6,000 plus $6,500, for a total of $19,500. In the second column, we use the net savings method with projects A and B. Using this approach, we add the net savings per project, $10,000 plus $7,000, for a total of $17,000. In the third column, we use the SIR method for projects A, C, and D. Using this approach, we add the savings to investment ratio for each project, $10,000 plus $6,000 plus $6,500 for a total of $22,500. This example shows that the savings to investment ratio method is the best method to rank and select among the 4 independent projects because it results in the greatest net savings. Now that we have shown that savings to investment ratio is the appropriate ranking method, let's consider a second example which assumes a $10,000 budget. There are 7 different alternatives A through G in this example. One of the projects, Project A, has an investment cost of $200 and present value energy savings of $900. Therefore, it has net savings of $700 and an SIR of 4.5. Another project, Project D, has an investment cost of $10,000 and present value energy savings of $80,000. Therefore, it has net savings of $70,000 and an SIR of 8. These projects have very different initial investment costs, ranging from $200 to $10,000. They also have very different net savings, ranging from $700 to $70,000. The total investment costs, if you were to adopt all 7 alternatives, would be $19,800. As a result, they have a large variation in savings to investment ratios, ranging from 4.5 to 12.5. Since all projects have an SIR of greater than 1, they are all life cycle cost effective. It would be preferable to undertake all 7 projects if funding is available. However, the $10,000 budget constraint points toward 2 options. For option 1, you can select all projects except Project D. In this option, you select 3 projects that have a lower SIR than Project D because the budget does not allow you to select Project D, and the projects with lower SIRs are still life cycle cost effective. For option 2, you can select only Project D because this project requires the entire funding budget. The total net savings for option 1 is $83,100. The total net savings for option 2 is $70,000. From an economic standpoint, you would select option 1 with the 6 projects because it leads to greater net savings. That concludes this course. In summary, life cycle cost analysis does not have to be difficult. You do not have to be a financial manager, budget officer, or economist to apply the best practices you have learned in this course. Use the tools and resources that have been demonstrated in this course to achieve your goals. You now have the knowledge required to improve decisions using life cycle economics, determine what requirements and data sets you need to get started, adjust cash amounts to present value, calculate life cycle costs and supplementary economic measures, evaluate efficiency levels among design alternatives, and allocate investment funding among competing projects. Lastly, if you have any questions about this course or are interested in other training opportunities, do not hesitate to get in contact with the Office of Energy Efficiency using the contact information provided. Our email address is enercan.greeninggovernmentvert.rncan@canada.ca. Our website can be found at www.enercan.gc.ca/greeninggovernment. Thank you for participating.